All right, howdy folks. Welcome back to Professor Carbon. In this video, what we're going to do is go over a bunch of reactions, and these are all going to be centered on either utilizing ketones or aldehydes or making ketones or aldehydes. And so with that, what I always encourage you to do is to take a few minutes and pause these videos. So please do that right now. Try to work through them all on your own. It's really your best opportunity to try to master the material instead of just listening to me narrate through the answer. So please do pause right now. As a really quick reminder as well, if you'd like access to these PDFs either in the blank format or filled out after the video, you can download those on our Patreon page. All right, so let's just dive in here to the top one, and let's see here. This is going to be a two-stepper, so we're going to have to think through what the intermediate is. Now, ozonolysis is a great way to cleave double bonds into their dicarbonyl, and here the DMS is going to help us reduce that secondary ozonide to the carbonyl compounds. And so let's just imagine clipping that bond there, and so we can then have a methyl ketone. And then let's see here, between that ketone, we need 1, 2, 3 carbons. So 1, 2, 3 carbons, and then we're going to have an aldehyde where the other position is. And so the aldehyde carbon is going to be this carbon, going to be that carbon there. So now the second set of conditions, so this should be, step 1 here. So 1. And then 2 is what we want to get to for the answer. Now for this, what we're going to end up doing, so any OH seems like somewhat innocent conditions. It's not a very complex reagent, but this is actually probably going to promote an intramolecular aldol condensation. And because it's an aldol condensation in the presence of that weak base, what we're going to do, weak here again for aldol parlance being something that has a pK of about 15, what we're going to do is push that forward and try to go all the way to the condensation product. Now, because this is technically a crossed aldol, where the carbonyl that we're going to make the enolate from is going to be different from the carbonyl that's going to be attacked, we should really consider a wide variety of enolates here. And so we could imagine deprotonating this carbon. So that would make this enolate. And I'm just going to color code these here then. So we can have this enolate. And then, believe it or not, we can also have this position on the aldehyde being enolate. And so there's actually 3 different potential enolates from this problem. And because of that, then we probably want to start considering what kinds of ring sizes we would make if this actually attacked itself. So we can imagine this attack. So that would be 1, 2, 3, 4. That's a pretty small strained ring. We can imagine here 1, 2, 3, 4, 5, 6. So let's just draw that out. So that would be 6. 6 is a good size ring to make. It's not quite as fast or efficient as 5, but it's still up there. And then lastly here, we could imagine this attack, and that would be 1, 2, 3, 4. And so with these enolates, remember the deprotonation is going to be an equilibrium process, and so we in principle could shuffle through all of these different enolates. And the one that's going to form the most facile product is actually going to be this one. And we're going to have a 6-membered ring then, so I'm going to start with that. And we're going to throw a ketone in there, and then we'll have the condensation onto that last carbon. And so there we go. So we'll make cyclohexenone from this process by preferentially cyclizing one of the 3 potential enolates. So that's kind of cool. All right, moving on down here, let me see what kind of conditions we have. Let's see, now this is an unusual phosphonium salt, and the good news is there's only one reaction that we typically talk about that has a P+ in it, and we have a nice strong base here in butyl lithium. Now butyl lithium is probably overkill for this reaction, but what it's going to do is deprotonate one of these hydrogens, and so we're going to end up with PH3P double bond phenol there. And so this is the illid intermediate, and remember that's in resonance with the P+ C- version. And the illid is going to be really good for the Wittig reaction, and so Wittig makes a double bond, and so we want to imagine chopping this double bond off. And since we have the phenyl over here, this is going to be the Wittig reagent half, and that means that wherever we started with here, we're going to want an oxygen on that part. And so that would be the answer I would put down. And then we could imagine that ketone being attacked by the ylide to complete the Wittig reaction. And I think that that checks out. All right, moving on to C. Let me see, we're going to add a phenyl ring, and we have this full backbone here in our starting material. And so that's the bond that we're going to need to make. And let's see here, this is going to be added at the 1,4 position or in a conjugate manner. And the good news is we should know a really great reagent to do these conjugate additions. And so this should be some lithium copper phenyl 2 species. And so that would be the kind of reagent that we would choose to do this sort of conjugate addition. Copper there is what's going to key up the conjugate addition instead of the 1,2 addition. So remember, if you used just old phenyl lithium, we would imagine instead that you would get out the phenyl group adding directly to the ketone. So, you know, the lithium or magnesium really go 1, 2, and they would attack here, whereas the copper reagent, so anything with copper, will go 1, 4 and attack at the distal spot. So that's an important distinction to make, and it's really a nice treat of being able to select what kind of reagent we want to make the product. Moving on down here. All right, so hydroboration, and then let's see here, NaOH plus peroxide. So this is going to make the peroxy anion. So that's going to do our oxidation. So we have hydroboration and oxidation. And so that's great. Now, we have an alkene, and so we could imagine then doing that hydroboration reaction. And it'll go in the anti-Markovnikov manner. So we'll add H and OH to different sides of the system. And so nothing wrong with that. The one hiccup here, though, is that this is an enol. And enols are not stable. And so if you were to write the enol on my exam, I would mark it incorrect. And the reason is that that enol will tautomerize. And so the answer that I would actually provide should be the aldehyde out after tautomerization. And so this is a nice way to go from the alkyne to an aldehyde by use of a reagent that hopefully we all remember from the alcohols and alkenes section. All right, next up we have our last problem here for this discussion. And this one's going to be a toughie. So sodium hydroxide, again, is a little bit too simple. And then we have a methyl vinyl ketone. And methyl vinyl ketone is one of these reagents that's really complicated to work backwards from. But hopefully we remember that it's the usual suspect for the Robinson annulation. And so I would suspect that this would be the product of a Robinson annulation. And the way then that we want to do that, remember, is it's the Robinson is first a conjugate addition. And the conjugate addition with an enolate is often referred to as a Michael addition. So you can call it either way. And then the second step is an aldol condensation intramolecularly. And so we got to think that through in the reverse direction. And so this is the double bond that we might make from the aldol. And so I then can imagine what that starting material would look like. And so if I had this dione, that would be able to undergo an aldol condensation here where this methyl group attacks after deprotonation to make the enolate, that carbonyl there. So that would connect that out. And then the Robinson annulation is going to have the first step is that conjugate addition or Michael addition. And so then on our methyl vinyl ketone here, these 4 carbons are going to be these 4 carbons. And so then the bond we're going to need to chop off is that one. And so then I should be able to go back to a monocyclic starting material. Here we go. And that would make sense. And the other thing that's nice about this is the H that I'm drawing here is going to be more acidic than the H out here. So I'll label this one A and B. And so A is more acidic than B because if you draw that enolate, from deprotonating HA, we can delocalize that negative charge not only into the enolate oxygen, but also into the aromatic ring that's over here. And so there's additional resonance structures that help stabilize the enolate from this position instead of the enolate from that position. And so that helps promote the initial Michael addition from that site regioselectively, and it's one of the nice attributes of these sorts of reactions. All right, so with that, that sums up a number of reactions here from the ketones and aldehydes section. Hopefully you've enjoyed the discussion. If so, please do subscribe to our YouTube channel. I've really been enjoying watching the number of subscribers grow, and so I hope that that continues. Please do provide a little bit more encouragement by subscribing. Again, if you want access to these PDFs, you can download them from our Patreon page. Please do like us on social media, give us a thumbs up, and tell a friend about Professor Carbon. Thank you.